Hello everybody and welcome to example 3. We are looking at the bottom of page 137 in the workbook here. Okay, and in this example we're going to try to use corollary 1 to write a vector as a linear combination of the vectors in the set S. Okay, so just so we don't have to keep scrolling up and down, I want to just write down the conclusion of corollary 1. Okay, so it basically said something like this, that y can be written as a linear combination of our vectors in S in the following way. Okay, so sum from 1 to k of the inner product of y with vi times vi. Okay, and the key here to being able to do this is that we have an orthonormal set. The problem, they're telling us that S is orthonormal, which basically just means that those vectors are mutually orthogonal and all have length 1. That's something that you could check just by taking dot products. Okay, now you might notice here that in this problem, the vi's that you see, those are really just the 3 vectors that are in our set. Okay, so we might make the observation before we start that k is really 3 in this problem. Okay, so let's start maybe by adjusting our sum. So we're really going from I equals 1 to 3. And the other thing we might notice is that we're calling the vector that we'd like to write as a linear combination x and not y. Okay, so let's change the y's in this to x, just so it's consistent with the notation that they're giving us in the problem. Okay, so corollary 1 kind of turns into that in our particular situation. And one other thing we could do just to make the notation a little easier, I'm going to call this inner product of x with vi ai. That's just the coefficient on the ith vector in S. Okay, so with that notation established, let's calculate those coefficients ai. All right, so a1 would be the inner product of x with v1, which means we're going to take the inner product of 4, negative 1, 1 with v1. Okay, so let's kind of highlight those 2 vectors. So we're going to take x here and take the dot product of it with v1. If you do that, this is basically just taking a dot product. We're going to get the 1 over the square root of 2 that you see kind of out in front here. And then we're going to take the dot product of the 4, negative 1, 1 with 1, 1, 0. That's going to just give us 4 minus 1. Okay, if we do that calculation. So we wind up with a coefficient that looks like 3 over the square root of 2 for a1. Okay, and then moving on to a2, that's going to be the inner product of x with v2. Okay, so now let's erase some of the markings that we have there. Now we're looking at the inner product of x, with this vector. So there's a 1 over the square root of 3 out in front. Okay, and if we take the dot product of the 4, negative 1, 1 with 1, negative 1, 1, you can double check my calculations there and see that that's going to give us 4 plus 1 plus another 1. Okay, put that all together, we're going to get 6 over the square root of 3. Okay, and then finally a3, same idea. You take the inner product of x with v3. You can confirm this. This time we're going to get a 1 over the square root of 6 out front. And let's see, a negative 4 minus a 1 plus a 2, if you put all that together. Okay, that's going to give us a negative 3 over the square root of 6. Okay, and so if we've done that all correctly, here's what that should mean. The x that we're starting with, the 4, negative 1, 1, that should be equal to our first coefficient times v1 plus our second coefficient times v2 plus our third coefficient times v3. Okay, and this is what they actually asked us for. Okay, so that's our answer. I want to just mention, though, that we could write that maybe in a little bit nicer of a form. Okay, if we go back up here, let me just erase some of the markings that we did here. Okay, notice that if you take this 3 over the square root of 2 and multiply it by v1. Okay, v1 is the vector up here. You can kind of put the 3 over the square root of 2 together with the 1 over the square root of 2, and if you multiply those, you get just a little bit nicer of a number. You get 3 halves, okay, times v1, which would be 110. Just another way of writing that first term. Okay, and then similarly, 6 over the square root of 3 times v2 would put 6 over the square root of 3 together with 1 over the square root of 3. Multiply those two fractions, you get 6 over 3, which is 2. Okay, times the vector v2, that's just, or the remaining part of v2, that is, 1, negative 1, 1. Okay, and then you can do kind of similar arithmetic on the third one and just rewrite that as negative a half times negative 1, 1, 2. Okay, that's actually equivalent, but maybe a little bit nicer to look at than what we have here. Okay, so I just wanted to mention that that's an alternate way of maybe expressing our answer.